Chapter 14, Kinetics, Exercise 14.63. The half-life for the radioactive decay of uranium-238 is 4.5 billion years. How long will it take for 10% of the uranium-238 atoms in a sample to decay? Over here, 10%. So what we can do is we first compute the rate constant. Alright, K is Ln2 over half-life. And we do have half-life, and then we'll get K. And then we'll use a second equation. So for 10% of the atoms to decay, that means we have 90% of the atoms left. This is going to be the concentration of the sample after a certain time period divided by the initial concentration, right? 90%, right? 90% left after a period of time. And this is going to be e to the power negative kt. So we use these two equations. And obviously we can compute k first. 4.5 billion years, so it's 4.5 billion years. So this is k, and then we solve this equation. But also we can combine these two equations. I think I'm going to replace this k with this expression. Let's see if I can do it. Alright, it's not too bad. Alright, so again, 0.9 is the concentration at time t divided by the initial concentration. Based on this information, it should be 90%. Alright, and then it's e to the power negative kt. And k is ln2 over the half-life, and then we compute t. How do we do that? I'm going to take the logarithm of both sides. Okay, and the logarithm of e to the power of this whole thing is just this. Alright, and I need a way to type it up. Okay, somehow I can't. So I'm gonna carefully select this part and do a negative sign here, and okay, now we're good. And you can see t is just ln 0.9 times 4.5 billion divided by negative ln2. That's the setup. Alright, that's the setup. That's t. Alright, I'm gonna just show you the individual calculations. Over here we have ln 0.9. Just want to make sure I take ln 0.9, and then finally divided by negative ln2. So this whole thing divided by negative ln2. This is the number 1 2 3 4 5 6 7 8. Okay, 6.84 times 10 to the power of 8 years, or 684 million years. Alright, over here, same, a bit rounding error here. Part B, if initially it contains this many atoms, and then after 13.8 billion years, how many atoms are there? I'm going to say it's x, and x is going to be 3.7, which is initial, times 10 to the power of 18, alright, and then multiplied by e to the power of negative kt. This is the setup. Alright, so this is how we compute the number of uranium-238 atoms after 13.8 billion years. So t is 13.8 billion, and k, we don't have k, but we have half-life, so k is ln2 over half-life anyways. Alright, let's just plug in this ln2 divided by half-life, which is 4.5 billion years, and t is T is 13.8. T is 13.8 billion years. Alright, that's it. We'll get 1.77 times 10 to the power of 18. That's the number of atoms. Oh, wait a minute. I need to get rid of this. And something really important, I want to compute ln2 first. And then do the multiplication. So I got 4.4 times 10 to the power of 17. Alright, 10 to the power of 17. So when in doubt, just use one extra pair of parentheses. So you compute ln2 first. And then multiplied by 13.8. Alright, so now we have this. Usually we use this equation for concentrations, but again, I mean, when we look at the same sample, we assume the volume is the same. So the concentration is proportional to the number of atoms. Alright. Okay.